So we are now recording. Let's pick up where we left off. Unless there, are there any questions? Related to physics or hideous diseases? Yes to all of that. The intent was not a hard and fast deadline from my point of view, but from getting it off your plate. So, my personal recommendation to you is get it done early instead of having to hang over your head over all spring break. Now, whether you actually scan it and email it, or take pictures and email it, or if you wait until you come back, either one's fine. Test corrections. Just don't tell Anna. All right. I believe we were just about to do AC power, AC circuits. We'll get to that. Probably. All right, so the symbol for an AC power supply is basically, it's a circle with a sine wave in it, or shifted cosine wave. I don't know. It is chapter 24? Yeah, I think it's chapter 24. Chapter 24 is when he goes into the speed of an electromagnetic wave. And let's say 24 for now. All right, so when you're dealing with AC power supplies, we do have two types of notations we need to deal with, uppercase and lowercase, and it's going to start to matter. So if I write I equals I cosine of 5t or something like that, the two i's both mean current, but there's some slight differences there. This is the instantaneous value. Current. And this is the maximum current. Sometimes there's a subscript, but generally, when you're dealing with uppercase, lowercase is for the instantaneous value, and uppercase is for a magnitude, for maximum value. Now AC power supply was going to have voltage going back and forth, and so you might see one of two notations. You might see V is equal to sort of capital V cosine or sine omega t plus phi. That's sort of the generic. Or instead of a lowercase v, sometimes you'll see an epsilon there. And then a capital epsilon. It gets kind of awkward. So some combination thereof, or you might see that's an epsilon there. So for whatever reason, we tend to use, I tend to use EMF now more than I did when dealing with DC. All right, questions on just basically notation at this point. All right, so let's take a look at a circuit, the R circuit. So basically I have a circuit with a resistor in it. I know that Ohm's law still matters here, that the potential going around, so I know that V is equal to IR. That is the maximum value is equal to the maximum current times the resistance. And also I know that instantaneously V is going to be equal to that whatever potential gain I have going across my power supply, I'm gonna have the potential loss going across my resistor. The important thing to recognize now is that this R here, resistance, this is just a number. So if the current across the resistor is, say, 5 amperes cosine of 4t, and my resistance is 4 ohms, then the potential difference across my power supply is just going to be, well, you multiply them. 20 volts cosine of 4t. This is not supposed to be earth-shattering. And then more importantly for what we're about to do, let's plot. If I plot the potential across the resistor, given that it's going to look something like this, where this would be 5/2. And then my current is going to look like this. Not necessarily the same scale. I probably should emphasize that by drawing it a little bit differently there. That's current. Now the reason why I have different amplitudes there is the fact that they're on 2 different scales. One's in volts, one's in amperes. But the important thing to see here is that they are in phase. They peak at the same time, they drop at the same time. The only difference is that one is an elongation of the other one. The fact that they are in phase will make a difference in a moment. Questions so far?
Absolutely way too loud.
All right, phasers. This is not the Star Trek weapon. That's spelled with an E. A phaser is just a way of visualizing what's going on in an AC circuit. So if this is a phaser right here. Imagine it is an arrow that is spinning around counterclockwise at some angular speed of omega. So this omega right here is the angular speed of the arrow of the phaser. Angular speed of the phaser. And it is the exact same omega as the angular frequency in our formula over there. So that same value. There's a philosophical difference between angular speed and angular frequency, but they look and smell the same. Possibly even taste the same. So, when dealing with a phaser, so if I had a phaser to describe this current right here, I draw the phaser anywhere because we have this phaser that's spinning around, and so where it actually is sitting is really dependent on how you want to draw it. So typically when you're drawing a phaser, it's in the first quadrant, but for no particular reason other than just have it. This phaser would represent 5 amperes because the magnitude of this should be the magnitude of the current. And if you project it down onto the horizontal axis here, this right here is the instantaneous value. And so whenever you're doing this, and you can see how it connects here, that we have some angle here, theta. And so this should be the magnitude times the cosine of the angle. And I know that omega is equal to the change in the angle over the change in time, or if you're starting from 0, theta over t. In other words, the angle is just omega t, which is what we have right here. The phi here is known as the phase shift. So if let's leave that there. I hope everyone at this point is familiar enough that this is a cosine curve. If I look at a sine curve, recognize that's just a shifted cosine curve. There's the cosine right there, except cosine typically starts at the maximum. And so what all the difference is, if I want to get from here to there, is I just need to shift this over, and I have a cosine. If I shift something to the left, then, let's make sure I put in the sign the correct way. So this is cosine of omega t, some amplitude times the cosine of omega t. This is the amplitude of sine times omega t. Then shifting it, this is also amplitude times the sine of omega t. And then it's either going to be plus or minus phi. Let's see. So plus pi over 2. Sort of as a, for one thing, if I'm shifting a graph left, it's plus. If I shift it right, it's minus. From another point of view, when time is 0 here, I want to be at the peak, which is the sine of pi over 2. So when time is 0, I want to be here, so basically I'm going to add pi over 2 to whatever this is. Questions here? Just setting a foundation with a lot of loose facts. We'll pull it all together. Much to your delight. Let's see, one other bit of background, and then I think we're ready to plunge into something more interesting than just a resistor circuit. And ultimately get to Eli span. All right, so I have this function right here that's oscillating back and forth. We'll just say an amplitude of 1, and so amplitude of 1. Now, if I'm dealing with voltage, I have this voltage going back and forth. Typically, since this thing in the US, the thing's oscillating back and forth 60 times a second, so knowing what the voltage is, instantaneous voltage at any particular moment, really doesn't make a lot of sense. So I need to know what the voltage is at 0.0001 seconds. And yes, you should be able to do that. However, in terms of everyday electricity, it really doesn't, it's not particularly helpful. What you do want is a changing of, you want current flowing, doesn't necessarily have to be flowing all in one direction, obviously. And so we need to figure out what is the average value. So if I have a function, and we can just take a look at just the first cycle here, what is the average value of this function from here to here?
0.
Yes. But that does not mean that our average voltage is 0 in the fact that nothing ever runs. I think hopefully you understand the fact that there is electricity running through these lights here. And so they came up with something that works better, that since the actual value is not as critical, first thing they did is they squared it so you have only positive numbers. Because the fact that this is negative is not particularly useful in terms of, is it going to make something run or not? Again, what you need is something moving, doesn't really matter which way it's moving. And so they square this, and so the function now looks like something like that. They find the average of this, which is going to be somewhere around here, and then they take the square root. So if you find the average of this, it turns out the average of this, actually should have been down here, is 1/2. And then you take the square root of that, and you get the square root of 1/2, which is the square root of 2/2, which is roughly 0.707 something. This is known as the RMS value, or root mean squared, which is basically the reverse order of what you actually do. Because in reality, what you do is you square it, you find the average or the mean, and then you take the square root. But it's called the RMS value. So the RMS value is equal to the square root of 2/2 times the peak value. So if I take the multimeter, it defaults comes up on DC here, but we want AC. So I switch it over, I click the select button, and it now says AC in the upper left corner. I'm measuring voltage here, and so now I can stick the leads into an outlet. And it's automatically assuming that we're talking about DC. And it says 124.2. If I had this thing on DC and I do it, what would you expect to happen? Because you've only used DC for this thing, but when you've measured voltages or resistance, and when you measured anything with DC, what is it actually measuring?
The voltage coming out or going in.
Yeah, I mean, either one. I'm going to throw one word at instantaneous. With DC, you assume it's steady, and so what it does is it measures the value at that moment, and then a tenth of a second later, or how often it does that, again, another moment, another moment, another moment. So if I do this, so if I put this thing into the outlet on DC, what would you expect the display to show?
One value.
Why one value?
Because since it's not changing, the voltage isn't changing.
Oh, it is changing. This is alternating current. The voltage is constantly oscillating back and forth.
You said DC.
If I had this on DC and I measured it into an AC outlet.
Oh.
Read my mind, come on.
You'd get an error?
No, it would not be an error.
Okay.
Yeah, all over the place. Unless, of course, this happens to be cycling, this measures at just the right moment every single time. So it is also possible that if I'm measuring DC here and it measures at this point, then at this point, this point, this point, it would come out as a steady value. If it's slightly off of that, then that point, then that point, then that point. Then let's find out what happens. Have you seen the anti-grav helicopter video from a couple years ago? It's basically a helicopter in the air and the blades are not turning.
Oh, because the frame rate?
Yeah, the frame rate happens to be just the perfect match for the rate at which the blades are turning.
That's so cool.
So it's on DC, and we're at, it's only going to millivolts here. So 54, 78, 16, 12, 10, we've got a 300 at one point, we're down to 4, 0 negatives now. -6, -9, and slowly creeping off in the other direction, shot to positive. So I'm assuming all of you have young eyes and you can see the display changing rapidly. All right, so for AC, it is assuming that it assumes that you're using it for 60 cycles a second. So if it's 60 cycles a second, oh, that's, sorry, amplitude, those are two different things. So in the US and various other countries, Europe is different standard. The frequency in the US is 60 hertz. So flashback to first semester, November, December, somewhere in there. What is the relationship between angular frequency and frequency?
They're inverse? Or
No,
like
frequency and period are inverses.
time period are inverses.
What are the units, what is a hertz?
Per second?
Pardon?
Something per second?
It is. What is the something? All right, pardon?
Wavelengths per second?
Cycles. Yeah, cycles. I was trying to see if you could stretch the wavelength into it. It's related to that, but I think you'd be hard pressed to make that stick. It's cycles per second. Period is seconds per cycle. In other words, you have repetitive motion. How long does it take for one of those cycles to happen? That's the period. Frequency is the flip of that. So this would be cycles per second. Or typically it would be written as 60 per second, or 60 1/seconds, or 60 seconds to the -1. Depends upon how fast or loose you want to play with the notation. What are the units of angular frequency? Hint, they are the same units as angular speed.
Meters per radian?
No.
Rad per second?
Say it again?
Rad per second?
Yes. So the units of angular frequency are radians per second. Let's clear some space here. That, all right. So the units of frequency, the SI units, is a hertz, or a cycle per second. And angular frequency, that is an omega, not a W, is a radian per second. So if we picture something that's traveling in a circle, how many radians are in a cycle?
2 pi.
So if we take this and multiply by 2 pi radians per cycle, we get this. So omega is equal to 2 pi times the frequency. So what I would expect is this, we aren't measuring frequency here, that's something for a lab, which we might or might not do. I assume all of you have AC power supplies at home as well as multimeters and the LabQuest equipment. All right.
One of those things.
One of those things?
Yes.
You have access to an outlet, is that the?
No, 2.
All right. See, if I wait a little bit longer, will it be 3?
No.
We could do group labs through the video. You would just do the lab and we get the data and watch you do
And it might come to that. I sort of pictured that I would get to grade if it truly is 2 weeks of spring break and not just a week of spring break and then back to online classes or or we have class on Monday and whatever it ends up being. I could very well see it's 2 weeks of my shooting video and doing labs in front of the camera. That'll be exciting. Ooh. I can just delete all the ones that get bad results.
There you go.
All right, so we are 60 cycles a second, and so the angular frequency I would expect would be 2 pi times 60 hertz, which ends up being 370, 369
376.991.
radians per second. And that's the part of the lab which you might or might not do. You'll be using the lab quest to measure voltage or current running through something with AC power supply. And you should be seeing something very close to that. And then back to the 124.2, this value here, when you are doing a measurement out of an AC power supply, it is trying to find you an average value, but not just the typical average, because as you said, the average would have been 0, the RMS value. And so this is the RMS value of the peak voltage. So V RMS, again, it is a specific value, so it's a capital letter, not a lowercase letter, is equal to 124.2 volts. And therefore, the peak value should be 124.2 volts divided by square root of 2 over 2. Or we can also write that as 124.2 times the square root of 2 volts, or actually do the math, and you get 169.
175.65.
0.65? So that is the peak voltage being out of that outlet. All right, questions at this point? Am I correct to assume complete understanding right now? That was a yes? All right, cool. All right, so now let's take a look at a more interesting circuit and talk about why phasors actually have some impact and importance here. And what this means. I had a different memory trick. This is a memory trick here. I had a different memory trick for it, but then one of my students said, oh, what she had been taught from another teacher was this, and that seemed to stick better. All right, so let's talk about an AC power supply. And this time we're going to throw a capacitor into it. This has some value here. So V is equal to some maximum value times, why not cosine of omega t. We typically, in board problems, we're not going to have a phase shift in there. In other words, it's just omega t, not omega t plus phi. In the lab itself, you will have a phase shift because you're going to be doing a measurement starting at some point there, and it's not like you can pinpoint it up. I only want to start it when it's at a peak or start it when it's at 0. So it is going to be, so board problems, we don't have a plus phi, but in lab we will have a plus phi. All right, so Ohm's law, voltage rule loop, not Ohm's, Kirchhoff's voltage loop still applies, so if I do a voltage loop around here, I should end up back at 0. So starting at this point, going clockwise. So I have the change in voltage across the power supply minus the change in voltage across the capacitor should be 0. From a DC point of view, if I have this hooked up to a battery, here's my positive and negative side. Negative side has the electrons, which show up on this plate, so that's negative, that's positive. And so as I go around the loop, I gain going across my power supply, then I'm going from positive to negative on the capacitor, so I lose going across the capacitor. Here, I really don't know what's the positive and negative side. It is helpful in a lab just to assume, all right, I'm just gonna make one of these positive in terms of keeping track of it. So I just automatically still go with the assumption that this is sort of the plus side, but it really does flip back and forth. All right, so voltage across the capacitor. What is the voltage across the capacitor? Or what is the definition of capacitance?
Charge over change in voltage.
And so therefore the change in voltage would be Q over C. And so what we have here is this epsilon cosine omega t minus, going lowercase since we're talking about instantaneous values, over C equals 0. I want to solve for Q. This is the thing that's fluctuating over here. And so Q would be equal to slowly dying marker. Q would be equal to, bring this over, multiply by C, so C times epsilon cosine omega t. So we now have a formula for the charge that's sitting on top of the plates. The charge on the plates is in sync with the cycle of the power. However, generally we don't care about Q as much as we care about the current. So the question is, if this is Q, what is the current? Well, let's go back to the stuff that we did the other day. If I have a cosine curve, what is the slope?
Negative sign.
So it's 0 here, here, the slope is 0 at those 3 points, so there, there, and there. So that goes to